In this video, we're going to introduce the unit circle. The unit circle is a special circle that's centered at the origin with a radius of 1. The unit circle is going to be a really handy tool for evaluating trig functions at these main angles. It's going to allow us to evaluate them quickly and exactly without having to use a calculator. So here's our unit circle. We've got a lot of information on here, so we're going to walk through each of these pieces. First, the innermost values are our degree measures for our angles. So just to illustrate 30 degrees, that's the angle in standard position that terminates at that spoke. Next, on the inside of our circle, the next value inside are the values that correspond to the radian measures of those angles. So in our last video, we were looking at, or in one of our previous videos, we were looking at conversions between degrees and radians. And there were examples where I mentioned soon enough, some of these conversions will just be memorized. So these are those conversions that are going to be memorized because they are going to be part of that unit circle. And then we have ordered pairs. Again, this circle is graphed on our XY coordinate grid. So we've got ordered pairs for each of these points along that circle. Now, within each ordered pair, the X and Y coordinates correspond to the value of cosine and sine for that particular angle. So this again echoes what we have in a lot of our tables. Remember, we knew that cosine of 30 degrees was the square root of 3 over 2, sine of 30 degrees was 1/2. As you continue to practice with the unit circle, there's some observations that you might want to make. There's a lot of patterns. I have not taken the time at this stage to have the unit circle memorized, but there are so many patterns that I know key values, and I can use those key values, particularly that first quadrant, in order to derive all of the other values. One quick observation is that we've got multiples of pi over 6. So 0 times pi over 6 is 0, times pi over 6 is 1. Then there's another pi over 6. Here's another pi over 6. Pi over 6, pi over 6, pi over 6. All these segments have the same angle measure of 30 degrees. And what we can do is we can use those multiples of 1/6 in order to figure out where we're at. So just to illustrate this, this is 0 over 6, 1 over 6, 2 over 6. 2 over 6 then simplifies to 1/3. 3 over 6 simplifies to 1/2. 4 over 6, 5 over 6, 6 over 6 is pi, 7 over 6, 8 over 6, 9 over 6, 10 over 6, 11 over 6, 12 over 6, and then we can continue. Similarly, we've got values of pi over 3. So here's 0 pi over 3, 1 pi over 3, 2 pi over 3, 3 pi over 3 are pi, 4 pi over 3, 5 pi over 3, and then 6 pi over 3 or 2 pi. And then pi over 4, 0 pi over 4, 1 pi over 4, 2 pi over 4 simplifies to pi over 2, 3 pi over 4, 4 pi over 4, 5 pi over 4, 6 pi over 4, 7 pi over 4, 8 pi over 4, so on and so forth. So just kind of knowing where those multiples of those pi over 6, pi over 4, and pi over 3 lie can help you derive a lot of these values. And then you are really using the idea of a reference angle. I will post a separate video illustrating how I derive values that are from the unit circle without having to memorize it. But if you're not interested and you have your own methods for knowing these values, that's really up to you how you proceed. But you do want to make sure that you know these values from the unit circle very well, or have a process in place to determine what those values are without having to go grab your calculator. Anytime a problem has some form of direction that says give the exact value, that's a good indicator that you should not be using your calculator, because anytime we grab our calculator, we're going to default to a decimal value, which is not going to be exact. So let's use the unit circle. I'm going to illustrate a few of these going back and forth to that unit circle, but you might want to have that unit circle printed out and handy just as a quick reference, especially while you're first learning the unit circle and getting more familiar with it. So we're looking for sine of 4 pi over 3. Now, 4 pi over 3, I'm thinking about that fraction of 4/3 is more than 1 pi. So I know that I'm in this bottom part of the circle. So just understanding those relationships allows you to not have to look at every single value on the unit circle. So 4 pi over 3 is a radian measure. Here's 4 pi over 3 radians. And this is our ordered pair, -1/2, -square root of 3 over 2. Remember that sine is always the y coordinate. A good way to remember that, cosine, sine, those are in alphabetical order, just like x and y. So sine of 4 pi over 3 is -square root of 3 over 2. Cosine of 4 pi over 3, well, that was our -1/2. We just saw that ordered pair. And then tangent of 4 pi over 3, tangent's not given, so we're going to have to use that quotient identity. Tangent is sine of theta over cosine of theta, which if theta is 4 pi over 3, sine of 4 pi over 3 divided by cosine of 4 pi over 3, which we have those two values here, -square root of 3 over 2 divided by -1/2, which is going to be positive square root of 3. And we know that tangent in our third quadrant is positive. Sine of -7 pi over 6. So using our unit circle, again, negative angles, we want to move clockwise. So I'm going to go, here's 0, pi over 6, -1 pi over 6, -2 pi over 6, -3 pi over 6, -4, -5, -6, -7 pi over 6 is this ordered pair right here. So I'm going to mark that ordered pair on that other page so that we can find our trig function values. So sine is our y value. This is 1/2. Cosine is our x value, -square root of 3 over 2. And tangent is sine over cosine, so 1/2 divided by -square root of 3 over 2, which is equal to 1/2 times -2 over the square root of 3. Our 2's are going to cancel out. Let me make that a little bit bigger, easier to see. I'm running out of space, but this is -1 over the square root of 3. And to rationalize it, we're going to multiply by the denominator over itself, square root of 3 over square root of 3, or -square root of 3 over 3. Find the exact values with angle measure 3 pi over 2. 3 pi over 2, rather than jumping back to that unit circle, 3 pi over 2. Remember that our conversion between radians and degrees, 180 degrees is pi units. So here's pi, which means this would be 3 pi over 2. So we're looking at that point right there. And if our radius is 1, this ordered pair is 0, -1. Sine is our y value, -1. Cosine is our x value, 0. And tangent is sine over cosine. So -1 over 0 or undefined. -17 pi over 3. We could look for a coterminal angle by subtracting multiples of 2 pi. It's really up to you how you want to do that. I'm just going to start using my multiples of pi over 3 and counting to 17s pretty quick. So let's go back to that unit circle to illustrate this. it's negative 17 pi over 3. So here's 0, negative 1, 2, 3, 4. I'm sorry, I've counted that wrong. 0, 1, 2, 3, 4, 5, negative 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this is equal to negative 17 pi over 3. So there's our ordered pair, 1/2 square root of 3 over 2. Sine is our y value, square root of 3 over 2. Cosine is our x value, 1/2. And tangent is sine over cosine, square root of 3 over 2 divided by 1/2, which is just the square root of 3. Using your calculator, approximate each trig function value. Again, make sure that you check the mode of your calculator. So I've shown you how to do this in Desmos. Again, if you hit that little wrench icon in the top right, you're going to see an option to toggle between degrees and radians in those settings. And again, the difference in these directions, this is looking for an approximation. If we look at the last several examples, we were wanting exact values. So exact values, again, not grabbing our calculator, using our unit circle knowledge. Approximations, we're going to use the calculator. So if I use my calculator to evaluate sine of 0.6109, we're going to round this to 4 decimal places. This becomes 0.5736. And for our next example, if our calculator was in radians, another quick reminder that if we don't have any degree symbol written there, we're going to assume that this is in radians. So in B, because we have that degree symbol, we want to make sure we go ahead and pause, change the mode of our calculator to degrees. And then cosine of negative 39 degrees is 0.7771 approximately. Find the exact radian measure of each angle within the given interval. Think what angle gives you this trig function value. So again, thinking about using exact or providing exact answers, we want to use that length or the knowledge of our unit circle. So in the interval from pi over 2 to pi, where is sine of theta equal to 1/2? So pi over 2 to pi, this is our second quadrant. This is Q2. So we're looking for an angle measure between or in quadrant 2 where the y value is 1/2. So we're going to go up here. We're in quadrant 2 and we're looking for a y value of 1/2. That's right here. Here's our angle 5 pi over 6. Find the angle such that tangent of theta is equal to the square root of 3. Theta is in the interval from pi to 3 pi over 2. This is quadrant 3, which follows because tangent's only positive in the first and third quadrant. Okay, so either this had to be the first quadrant or this had to be the third quadrant. Now, we've seen a lot of these trig functions for tangent set up and simplified. So hopefully we sort of recognize that square root of 3 value. But what we want to do is set this up as a ratio of sine over cosine. So tangent theta is again equal to sine theta over cosine theta, which we want to simplify to the square root of 3. So in order to get the fraction of the sine over the cosine to simplify the square root of 3, what we want is the square root of 3 over 2 and 1/2. in the numerator and the denominator. The 2's in the denominators will actually cancel out. But because we're in the second quadrant, we want them both to be negative. So again, now we're looking in quadrant 3 for where cosine's negative 1/2, sine is negative square root of 3 over 2. In our third quadrant here, there's our values for cosine and sine. So our angle is 4 pi over 3. Find the exact radian measure of each within the interval 0 to 2 pi. So in the entire circle, sine of theta is equal to negative square root of 3 over 2. Now, if we go back to our unit circle, which I'll pull it back up in a moment, what we'll notice is that there's a lot of repeated values, and even repeated values with the same sign, depending on where or the value of our angle. So sine of theta is negative square root of 3 over 2. That's our y value. If sine is negative, that means we know we're in quadrants 3 and 4. So we're going to end up with two angle measures that have a sine value of negative square root of 3 over 2. And they're going to occur in that third and fourth quadrant. So again, sine is our y value. So where do we have negative square root of 3 over 2? We have it here at 4 pi over 3. And if you look across, it also happens at 5 pi over 3. Again, this is a coordinate grid. So if we think about this, here's our y-axis, that's our horizontal line, but our y-axis is here in blue. So this horizontal line, anywhere it intersects the unit circle, is going to have the same y value. So theta is equal to 4 pi over 3 and 5 pi over 3. Tangent theta is equal to negative square root of 3 over 3. Again, we need to be a little bit aware of what ratio of sine and cosine results in a simplified version of tangent to be negative square root of 3 over 3. What this ends up stemming from is this is negative 1 over the square root of 3, which is then negative 1/2 over the square root of 3 over 2. And I'm actually going to do plus or minus 1/2 plus or minus negative, or plus or minus square root of 3 over 2, because that negative tangent value can happen when sine is negative, cosine is positive, or vice versa. So tangent being negative, this is Q2 and Q4. Remember that tangent is sine of theta over cosine of theta. So we're in quadrant 2 and in quadrant 4. Our cosine was square root of 3 over 2. So our x was square root of 3 over 2. Our y was 1/2. So that's going to be here at 5 pi over 6. And directly across, we have the same values for the order of pairs, just opposite signs. So 11 pi over 6 is our second angle. So a little bit more on the inverse trig functions on our calculator. We have used them in the past, but in the problems that we've seen, we sort of created the problem so that it yielded the specific answers from that trig function. What I mean is that our trig function is always going to return a value in a certain interval. And we'll talk a lot more about inverse trig functions in Unit 3. But for now, we just need to understand that our inverse trig functions are only going to give us angle measures in a certain interval. So for inverse sine, it's always going to give us an angle measure in this interval negative pi over 2 to pi over 2. For inverse cosine, it's always going to give us an angle measure between 0 and pi. And for inverse tangent, it's always going to give us an angle measure from negative pi over 2 to pi over 2. Quickly observe the difference between the interval for inverse sine and the interval for inverse tangent. Inverse sine, we do include those values of negative pi over 2 and pi over 2. In inverse tangent, we do not. Again, the explanation for why will be forthcoming when we start learning more about the properties of these inverse trig functions. Well, let's see how this is utilized in our work here. An arc length S lies on the unit circle x squared plus y squared equals 1. So that's just the equation of our unit circle. It's a circle centered at 0 with a radius of 1. Starting at the point 1, 0 and ending at the ordered pair xy, if S is equal to 2.5, find x and y. Now the hint here is that x is equal to cosine of our arc length and y is equal to sine of our arc length when using the unit circle. So let's talk about why that is. So a quick understanding here. We know that S is equal to theta over 2 pi times 2 pi r. This is our fraction of our circle in radians multiplied by the circumference. Now, if we simplify this, we get S is equal to theta times r, but we know that the radius of a unit circle is 1. So this tells me that S is equal to theta. So the measure of our arc length is actually equivalent to the number of radians for our central angle. All right, so now let's start working with this problem. Let me draw a quick sketch of our unit circle. These are 1, 0, 0, 1, negative 1, 0, 0, negative 1. The arc length is given to be 2.5. So that means that theta is equal to 2.5 radians. Now, where does 2.5 radians lie on this picture? We know that our negative x-axis, that point negative 1, 0 is pi radians. Pi is approximately 3.14 radians, which means 2.5 is going to be a little bit less than that. We could also argue or further explain that the positive y-axis is pi over 2, and pi over 2 is approximately 1.57. So 2.5 is going to be between those two values. So what we're trying to find is this ordered pair x, y. We know that x is equal to our value of cosine theta and y is equal to our value of sine theta. And we know theta is the same as our arc length. So this is going to be cosine of 2.5 and sine of 2.5. Again, make sure that your calculator is now switched to radians. This is negative 0.8011, and our y value is 0.5985. A negative x and a positive y are the signs for any ordered pair in the second quadrant.